Oh no, there's been a disaster, and I'm out of fuel. All I have is this useless plastic waste lying around.
It's a shame we can't use all this plastic waste to make a viable fuel for our engines and heaters. Oh wait, we can!
What? How?
We can help with that.
We are Team 2570, the Radical Refiners.
Our mission was to develop a portable pyrolysis refinement system.
This was a Phase 2 project designed to work alongside a portable pyrolysis reactor.
Natural disasters such as the 2023 Maui wildfires and hurricanes that ravaged the East Coast in 2024 leave affected communities without the necessary resources to power basic equipment such as those for transportation, heating, and cooking.
Thanks to Peak View Solutions, our team was successfully able to develop a process that converts pyrolysis oil into viable fuel products.
Pyrolysis is the breakdown of covalent bonds within organic compounds to make smaller organic matter. It's done in the absence of oxygen to not promote combustion under the extreme heats. Here, we are breaking down the carbon-carbon bonds within plastic to create smaller chains of hydrocarbons that are more easily combustible, which is necessary for fuel.
Batch distillation is a method of separation that utilizes the different boiling points of a liquid mixture to achieve separation. As the temperature of a mixture is increased, lighter components will be boiled off first and exit the top of the distillation column. Heavier components of the mixture will vaporize later at higher temperatures. The bottoms product is what remains after the distillation process is complete and is made of the heaviest components of the mixture.
Phase 1 of this project was able to produce a potent liquid hydrocarbon product. However, the composition of this liquid product is not viable for use in traditional combustion engines.
Typically, fuel used in gasoline engines contain hydrocarbons with carbon lengths from C4 to C12.
I'm a carbon atom.
However, this product from polyethylene produced a liquid with carbon chains ranging from C8 to C28.
I'm a carbon chain.
Diesel is a fuel already containing heavier hydrocarbons ranging from C8 to C21.
The target composition was determined based on ASTM standards for the desired carbon chain length, density, energy density, and cetane value. We intended to modify these characteristics through a distillation process, as is typical for fuel refinement.
Using Aspen Plus, our team was able to model our distillation process. Take a look.
This is our full simulation. We have 4 main components. We have a condenser coming out of the reactor, a heating pot, a column, and then another condenser condensing the products into the 3 collection vessels.
Let's take a closer look at the column now. Our pot uses an electric heater heating from the base to promote convection in the column and drive vapors up the column. The column is then a packed column, which is limited to 6 feet tall so that it is still portable and can fit in the bed of a truck. Because of this, the pack section of our column is limited to 4.5 feet of packing material, which limits our separation, but given appropriate run conditions, we are still able to achieve proper separations. At the top of the column, our product then moves into a condenser. From the condenser, it is then condensed into our 3 separate collection vessels. The switch between these 3 collection vessels to separate our products is based on the temperature at the top of the column. This temperature tells us what products are coming over at what time.
This way, we can control which carbon chain lengths are collected into each collection vessels. For our purposes, we separate our lighter compounds into the first collection vessel, labeled Key 1, and our heavier carbon chains into Key 2 for diesel composition. The heaviest carbon chains are collected into Key 3, which should be rerun through the pyrolysis process to be further broken down into smaller chains. This refinement process would require an initial input of diesel fuel to begin operation. However, based on the calculations from our Aspen simulation, this process would produce more fuel than is consumed per each batch run.
The main diesel product had a final density of 0.758 grams per milliliter and had a calculated cetane value of 49.17. This falls between the Chevron standard limits of 30 to 55, and given variable run conditions, the cetane can be adjusted down into acceptable conditions using our BOD 3 through 8 additive. This is a common additive used in the diesel industry, which is why it was chosen for our product. Given our 10-gallon or 37.9 liter input, our products came out to have 2 liters in the light key, 23.7 liters in the mid key, and 12.2 liters in the heavy key. This heavy key again will be recycled, so this will be counted into future mid key products. To ensure our simulation was as robust as possible, we had to know the composition of our pyrolysis oil. To determine this, GCMS testing was performed on the precursor oil. In addition to determining the composition of our oil, the GCMS testing also informed us that there was no toxic compounds such as benzene, toluene, ethylbenzene, or xylene present in our oil. This is important because these are normal toxins that are present in fossil fuel refinement.
Pictured here is a visual on how we analyzed our gas chromatography mass spectrometry, or GCMS, results. The top left red graph is an image of a gas chromatogram captured from the unrefined pyrolysis oil sample. Each peak observed on the top graph is associated with its own mass spectrum, as seen by the yellow graph below. A mass spectra is comprised of two main parts. First, there is the rightmost peak, which is indicative of the mass of the compound captured in the spectra, and then to the left, all the fragments of the compound as it is broken down by the machine. All compounds possess their own mass spectra due to the effects of the compound's unique properties on how it fragments. The mass spectra from the data is then manually matched to a database of known compound mass spectra pairings. The graph on the right is a mass spectra of 1-decene pulled from the National Institute of Standards and Technology. Using the previously described method, we were able to confidently identify 42 compounds within the unrefined pyrolysis oil sample from the pyrolysis reactor. The smallest compound identified was octene, comprised of 8 carbons in a chain with 1 double bond. From there, the list of compounds increases by 1 carbon at a time and consists of both alkane and alkene versions of the compounds until the largest compound, octocosene, which is 28 carbons with 1 double bond. This table was then used as inputs into our simulation.
Q1 is composed of shorter carbon chains, which is ideal for kerosene products and can be used in portable heaters and lanterns.
Key 2 is our target product, the diesel, which has the most volume and will be used as the final product to power generators, engines, and other small vehicles.
Key 3 is composed of longer carbon chains that are not viable for fuels, so these will be further broken down and used in future distillation processes.
This work so far focused on the pyrolysis product from pyrolyzing polyethylene. However, there are many types of plastics that will be available in a disaster-like scenario. Future work should entail exploring the possibility of other plastics and their pyrolysis oil products. These oil products would have a different composition from what we've explored so far and would require different parameters for the refinement process.
So thanks to the Radical Refiners and PQ Solutions, I really can use all of this plastic. Yippee!